In the next two chapters, one of the things that we're going to be working on is a concept called stoichiometry. And stoichiometry is extremely important for chemists and for society in general. Here we have an example of something called salicylic acid reacting with acetic anhydride to form aspirin, which there's lots of aspirin tablets produced every day. And what this chemical reaction essentially says is if you take one atom of this and one atom of this, or their molecules, excuse me, one molecule of salicylic acid with one molecule of acetic anhydride, you'll make one molecule of aspirin. Said another way, if we know how many molecules of salicylic acid we have and how many molecules of acetic anhydride we have, we can predict how much aspirin we will make. This is incredibly useful because if I work for Bayer Aspirin Company and I know I need to produce a certain amount of aspirin for the aspirin that people are going to consume, I can figure out how much acetic anhydride and salicylic acid might be required to make that aspirin. So stoichiometry is incredibly useful, but it's not something that one learns in one step. Essentially, we're going to learn it in several steps. And what we're going to look at in chapter 3 are some of the initial steps required for stoichiometry. In fact, 2 out of 3 of the steps required. And then we're going to learn some other concepts that can apply to those similar types of things. And then in chapter 4, we'll look at stoichiometry itself. So it's really important that you practice the concepts you're going to learn here because they will come up again and they're extremely useful in stoichiometry. So the first concept that we have to think about is counting by mass. And here I use an example from childhood of jelly beans. So it wasn't a jar like this, but when I was a kid in elementary school, around Easter time, they would put a jar of jelly beans in the lunchroom. And then one day of the year, every kid would get a chance to guess how many jelly beans were in the jar. And the student who got closest to the actual number of jelly beans would win the jar of jelly beans. And when I was a kid, I'd have some pseudo-scientific, what I thought was scientific way of figuring out how many jelly beans were in the jar. But at the end of the day, I was just guessing. But with a little bit more scientific thinking, we can think about how we might figure out how many jelly beans are in this jar. Well, if we look here, the easiest way to figure out how many jelly beans are in the jar without counting them is to count by mass. And this is done every day. But basically, what you do here is you weigh a representative sample of jelly beans. There's probably 40 or 50 jelly beans in this representative sample, but not overwhelming to count. Measure the mass. Then measure the mass of all of the jelly beans. Then just do a simple division. That'll tell you how many jelly beans are in the jar. So, for example, if this weighs 10 grams and this weighs 1,000 grams, you could figure out exactly how many jelly beans are in the jar because there's 100 times more in here than there are in here. So if you had 50 here, you have 5,000 here. So that's basically how it works. And counting by mass is helpful if you're doing jelly beans. The gloves that we use for our chemistry labs, they're packed in boxes of 100, and it says right on the box, packed by mass. So if you count them, you might get 99 or 101. No one's actually counting all of those gloves. They just know approximately what 100 gloves should weigh, and that's the mass that they put in the jar. Now, when it comes to chemistry, counting by mass is not only convenient, it's the only possible way. You can't count atoms. Atoms are way too small, so we have to count them by mass. We cannot count them by actually counting them. It's theoretically possible to count this jar of jelly beans. It'd be a pain in the butt, but it wouldn't be impossible. And if you only had to do one, it's arguably not that bad. But if you had to make 1,000 jars like this, counting all of them would be too much work. But when it comes to atoms, you just can't do that. There's another problem with atoms, though. The problem with atoms is there's just a lot of them. 18 milliliters of water has about 6 times 10 to the 23 atoms in it. So this is a huge, huge number and an overwhelmingly big number that we don't want to have to deal with. And it turns out that in many things in life, we use numbers of convenience. Numbers of convenience are essentially Convenient for whatever reason. Sometimes that reason isn't known to me, but they are what they are. A dozen is a number of convenience. You could go to Dunkin' Donuts and buy a dozen donuts. You can go to the grocery store and buy a dozen eggs. You could buy a dozen beers. For whatever reason, for certain things, 12 of them seems to be a number of convenience. When it comes to paper, a ream is a number of convenience. And a ream is it's many things, but it could be 500 sheets of paper. The most common ream, from according to Wikipedia, is 500 sheets, although it does have other numbers like 480. But a ream is a convenient amount of paper. Imagine how inconvenient it would be to go to Walmart and buy sheets of paper one at a time. That's horribly inconvenient. So what they do is they sell a ream. Imagine being in line behind somebody buying sheets of paper one at a time when they needed 200 sheets of paper. That would be, you'd be in line forever. In chemistry, the number of convenience is the mole. And mole, like this, is often abbreviated with this, where we drop the E for whatever reason. 1 mole, or 1 mol, is 6.022 times 10 to the 23 things. Note that just like a dozen, it does not apply to a specific thing. You could have a dozen donuts or a dozen eggs or a dozen beers. Those are all a dozen. It's 12 of them. It doesn't matter what it is. A mole is the same thing. Now, you could have a mole of zinc or a mole of water or a mole of anything else. If you were an extremely rich person, you could have a mole of dollars. That's more dollars than there are. So you cannot have, no one person would have a mole of dollars. This is a huge, huge, huge number. However, it is a number of convenience in chemistry. And here's why. The reason that a mole is, well, before I explain why a mole is a number of convenience, let me just give you a little bit of an idea of how big that number is. In a single drop of water, as shown in this picture, there are 100 billion times more molecules than there are the number of people on Earth. So this mole is a huge number. Said another way, atoms are really, really small things. So why the mole is convenient is because it relates atomic mass units to grams. And the mole, 6.022 times 10 to the 23, is called Avogadro's number, after the scientist who discovered it. So a mole relates atomic mass units to grams. So one atom of carbon has an atomic mass of, on average, 12.01 atomic mass units. However, 1 mole of carbon atoms has a mass of 12.01 grams. It's impossible to measure the mass of an atom, but it is not impossible to measure a mole of atoms. 12 grams, any usual balance found in a chemistry lab, an analytical balance or otherwise, can measure 12 grams. So this is a mole of carbon. If we look at magnesium, a mole of magnesium, 6.022 times 10 to the 23 magnesium atoms, has a mass of 24.3 grams. If you look here, that is the molar mass of magnesium from the periodic table. Similarly, copper, 63.5 grams, and copper here, 63.5 grams. Note that this is one decimal place. These are two decimal places. They're rounded slightly differently, but this is basically how it works. So this is 1 mole of any atom is the molar mass from the periodic table in grams. This is extremely convenient because we can measure grams. So we need to know how many atoms there are because stoichiometry requires that we know how many atoms there are to predict how much product we can make or how much starting material we need to have to make a certain amount of product. We can't use actual numbers of atoms by counting because they're too small. Just like in the case of the jelly beans. Counting all those jelly beans in the jar is a pain in the neck. So we don't want to do that. So we're going to do it by mass instead. And then the mole is a number of convenience. Instead of talking about individual atoms, we talk about moles of atoms because it relates their masses in atomic mass units to their masses in grams, which are much more manageable numbers for actual people in actual labs who are dealing with things at a large scale. we can't deal with things at the atom size scale. It's just not possible. So we have a lot going on here, but basically the logic is we count by mass, we use moles because it's more convenient than using actual atoms because there's just too many atoms. Just like it's inconvenient to buy paper one sheet at a time. So let's look at what happens if you have compounds. We've talked about atoms and their molar masses. What about compounds? Well, if we have CHCl3, well, we need to add each of the atoms in the compound together to find the overall molecular or molar mass. So we take 12.01 for carbon, 1.08 for hydrogen, and then 3 times 35.45 or 106.35 because there's 3 chlorine atoms. And we add those all together and we find that the molar mass of, this is chloroform, is 119.37. So this is how we find molar masses. We could do this for other types of compounds. Let's say we wanted to know the molar mass of table salt, NaCl. Well, NaCl is an Na, a sodium, and a chloride. So we take the molar mass of sodium, which is 22.99 grams, and we add to that the molar mass of chlorine, which is 35.45 grams. And when you do this math, you find out that the molar mass of sodium chloride is 58.44 grams. And this is the molar mass. We can write this as an equality. 58.44 grams of NaCl equals 1 mole of NaCl. So this is our equality between grams and moles. Let's look at another example. Let's look at water, H2O. So water has 2 hydrogens. Each hydrogen has a mass of 1.01 grams. So we take 2 times 1.01 grams plus 16.00 grams. And when you add those together, you get 18.02 grams. And what this means is that 18.02 grams of water is exactly equal to 1 mole of water. Again, we're using the mole because it's a number of convenience. We don't want to use atoms of water, or molecules actually, molecules of water, because it's just too big of a number. Just like we don't want to buy paper one sheet at a time. So instead we buy 500 sheets or a ream. So this is how we can calculate molar masses of any compound known to man. All compounds are made of elements, and the masses of all elements can be found on the periodic table. On any exam in this course, you get a periodic table. You are certainly not expected to memorize these molar masses, although potentially by the end of this course, you'll have the molar mass of water memorized. So that just gives you some kind of idea of how we calculate these things. Now going back to the lecture slides for a minute, I want to look at a few questions, some of which are here and some of which are other places. So we may not have 1 mole of water or 18.02 grams of water. We may have a different amount of water. So let's look at a case where we have, let me just get set here, 15.0, nope, not 15.0, 15.2 grams of water. And we want to know how many moles of water is that. Well, here, usually I suggest that we make a plan of attack when we're doing these types of things, like in other types of dimensional analysis problems. We're just converting the units. 15.2 grams of water is roughly 15 milliliters of water, and it's a certain amount of water. It's also a certain amount in moles, but it's the same amount. So this is a dimensional analysis. We're converting the units, but we're not really converting the amount. So how do we do this? Well, we need a plan of attack. I suggest we start with a plan of attack, even though it's in this case, a one-step conversion. So we want to convert from grams of water to moles of water. And in order to convert from grams of water to moles of water, we need an equality. And we get that equality from the periodic table. In fact, we just did it. We took the oxygen, 16.00, and we added that to 2 times the hydrogen, 2 times 1.01 or 2.02, and we find that 18.02 grams of water equals 1 mole of water. So starting with 15.2 grams of water times, we need to put one of these on the bottom and one on the top. Well, we want grams of water to cancel out, so we better put grams of water on the bottom. So we put the 18.02 grams of water, which we figured out from the periodic table by adding the 2 hydrogens and the oxygen together, and we put that on the bottom. On top, we put 1 mole of water. We then use our calculator and we find 0.843507 and some more numbers grams of water. This is 3 significant figures. This is a measurement. The one is not a measurement because it's exactly 1 mole equals 18.02 grams. This is a measurement. So 3 sig figs, 4 sig figs, we're dividing. So we do 3 sig figs. We need to round up because this 3 is followed by a 5. So we find that there are 0.844, make this a little bit more clear, 0.844 moles of water in this particular question. So if we want to convert from grams to moles, we need a periodic table. To do stoichiometry, you must be able to convert from grams to moles. So it's really important to practice with this. Let's look at another example. In fact, we're going to go the opposite direction. Let's say we have 0.67 moles of magnesium hydroxide, which is found in milk of magnesia, and we talked about this a little bit in the previous chapter. And we want to know, what is the mass of that? How many grams of MgOH2 are present in 0.67 moles of MgOH2? Well, our plan of attack here is again a one-step conversion. So we're going to start with we're going to start with moles of MgOH2, and we're going to convert that to grams of MgOH2. And in order to make this conversion, we need an equality. Our equality comes from the periodic table. So the first thing we need to know is that whenever you're using the periodic table, it's always 1 mole. So 1 mole of MgOH2 is going to have a certain mass. Well, how are we going to figure out what that mass is? Well, how we're going to figure that out is add up the magnesium. Note that it's 2 oxygens and 2 hydrogens that we're going to add to it. So we're going to take the 24.31 grams, which is the mass of magnesium, plus 2 times the 1 inside, oxygens, 2 times 16.00 grams, plus 2 times the 1 hydrogen in each hydroxide, or a total of 2 hydrogens, 2 times 1.01 grams. So we're going to add all those together. And when you do all that math, you're going to find that it's 58.33 grams. So 1 mole of magnesium hydroxide is equal to 58.33 grams of MgOH2. Note that if you have anything in parentheses, you multiply this subscript by this subscript. In this case, these are both 1. If this was 3, though, then you'd multiply 2 times 3 and you'd get 6 hydrogens. It's not, but if it was, that's what you would do. All right, so now we have our equality. So we have our plan of attack. We're going to convert from moles to grams, and we have our equality. Now we'll just start with what we start with. So we're given 0.67 moles of MgOH2 times, we want moles to cancel out. So we put the 1 mole of MgOH2 on the bottom. So we want moles to cancel out, so we put moles on the bottom. We then put the mass, 58.33 grams of MgOH2 2 on the top. Multiply by the top, divide by the bottom, and what you find is the calculator tells you 39.0811. And then some more numbers. In this case, we want 2 sig figs here, 4 sig figs here. Remember, the 1 mole is exact. It's exactly 1 mole equals 58.33 grams. So we want 2 sig figs in our answer, because this is 2, this is 4, so we want 2. This is the digit we care about. Since this is a 0, we put 39 grams of MgOH2. I strongly recommend that when you're taking notes here, you do write down the unit and the formula, because it'll be much easier to remember what you did later on. So I strongly recommend you write down all of the units so that when you look back at it, it's easier to remember what you did. Let's look at another example. Let's say you have 1 times 10 to the 12 gold, AU, atoms. And you want to know how many grams of gold that is. So let's say somebody says, I'll give you 1 times 10 to the 12, that's a trillion. A trillion gold atoms. You'll say, well, what's the mass of a trillion gold atoms? Is that a lot of gold atoms? You're going to find out it's not very much gold atoms, but we're going to take a look at it anyway. To do this, we need to find gold on the periodic table. But before that, let's get our plan of attack. Here we're given atoms, and I'll be honest with you, chemists don't often use atoms. It's not to say it never happens, but it's not that common. It is common in this chapter in general chemistry books, but it's not that common. It's somewhat like the equivalent of buying pieces of paper one at a time. In most cases, you don't want to do that, but maybe in some specialized cases where you only need a couple of sheets of paper, you would. So it's the same thing with this. But here, I do want to show you how to do it. So we want to convert from atoms of AU, because we're given the trillion atoms, and we eventually want to get to grams. But we don't know any direct relationship between atoms and grams. But we do know a relationship between atoms and moles of gold. And then we know the relationship between moles of gold and grams of gold. So we're starting with atoms, and we're eventually getting to grams. Intermediately, we're going to get moles. Now, what we need to remember here is that 6.022 times 10 to the 23 atoms of gold equals 1 mole of gold. Now remember, it does not matter if it's gold or if it's a molecule like water or whatever it is. Avogadro's number is not specific to anything. It's like a dozen, 12 donuts, 12 beers, 12 bagels, whatever. All right, you can have Avogadro's number of the atoms. So now that we know how to convert from atoms of gold to moles of gold, we now want to convert to grams of gold. To do that, to go from moles to grams or grams to moles, you need a periodic table to find the relationship. And right here, we find gold on our periodic table, and we find that 1 mole of gold equals 196.97 grams of gold. Now, we're going to make 2 conversions, and we have 2 equalities. We're good to go. Starting with the number given, 1.000 times 10 to the 12 gold atoms times. Well, we want atoms to cancel out, and we have atoms here, so we need to put Avogadro's number on the bottom, 6.022 times 10 to the 23 gold atoms, and on top, 1 mole of gold. For the second conversion, we have moles of gold, and we want moles of gold to cancel out. So we put 1 mole of gold at the bottom and 196.97 grams of gold, the unit we're ultimately looking for, on the top. To do the math, multiply by the top, divide by the bottom, multiply by the top, divide by the bottom. On Alex, you will find, excuse me, a link that will show you how to use the calculator to input these numbers, whether you have a Texas Instruments or a Casio calculator. So when you're using exponents, you do need to use the calculator for that. And there is a link to that on Alex and the problem where you have to actually do this. So that'll give you some practice with that. But take this, multiply by 1, divide by this, multiply by this, divide by 1, and the calculator will tell you 3.2874446 dot 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 some more atoms times 10 to the minus 10. This is 4 sig figs, this is 4 sig figs, this is 5 sig figs, so your answer should be 4 sig figs, and the best answer here is 3.287, we don't round up because that's a 4, times 10 to the minus 10 grams of gold. Okay, this is less than a nanogram. So if somebody offers you this, this is not a lot of gold. All right, you couldn't even see it. So this is basically some conversions. I do want to do one last conversion where we convert from grams to atoms to give us practice with that. So I do want to do that, and then that'll be the end of this particular section. So let's say that we have 9.0. Let me pick a different one. 8.5 grams of ammonia, NH3. And we want to know how many moles of NH3 that is. So instead of moles, actually, I apologize. Let me try this again. Let's say you have 8.5 grams of NH3, and we want to know how many molecules of NH3 that is. So, in order to do this, we need to do several conversions. First, we need to convert from grams of NH3 by way of a plan of attack to moles of NH3, and then finally to molecules of NH3. So once we have our plan of attack in place, we need, of course, our equalities. So for our equalities here, grams of NH3 to moles of NH3, nitrogen has a molar mass of 14.01 plus 3 hydrogens, which are 1.01 each. So we take 14.01 grams plus 3 times 1.01 grams, and we get 17.04 grams. That tells us that 17.04 grams of NH3 is equal to 1 mole of NH3. Next, we want to go from moles of NH3 to molecules of NH3. Here we want to use Avogadro's number. 1 mole of NH3 equals 6.022 times 10 to the 23 molecules of NH3. Note, in the previous case it was atoms of gold. Now it's molecules of NH3 because NH3 is a compound, not an atom. Now we have our two equalities, starting with 8.5 grams of NH3 times. We want grams to cancel out, so we put the 17.04 grams of NH3 on the bottom, and we put the 1 mole of NH3 on the top. Times. Now we want to convert those moles to molecules. So we want moles to cancel out, so we put the 1 mole of NH3 on the bottom and the 6.022 times 10 to the 23 molecules of NH3 on the top. We now have our dimensional analysis set up. Here, I'm going to do the sig figs first. So we have 2, we have 4, we have 4. The answer should be 2. So 8.5 divided by 17 is roughly a half. 1/2 times 6 times 10 to the 23 is roughly 3.0 times 10 to the 23 molecules of NH3. So in these past 4 examples, you have all the cases. Grams to moles, moles to grams, molecules to grams, grams to molecules. Chemists much more typically do grams to moles and moles to grams than they ever convert to molecules, because the number of molecules is just such a massive number, and this is in a relatively small number of grams of ammonia. We have a massive number of molecules. It's not very convenient. The mole is a number of convenience, and chemists like to use it.